Hi, this is Tzvi Rosen with another lecture on the history of calculus, and in today's lecture we'll be discussing Gottfried Leibniz. As we discussed in the last lecture, there were two recognized inventors of calculus, Sir Isaac Newton in England and Gottfried Wilhelm Leibniz in Germany. And we spoke about Newton and his process of producing the fluxions. Today we're going to focus on Leibniz. So let's look at a quick summary of his life. He was born in Leipzig, Germany in 1646, and he studied law and philosophy as a university student in the University of Leipzig. He was an outsider to the science world. He worked as a diplomat, a lawyer, assessor, secretary, librarian, but not as a professor at a university, the way that Newton had the Lucasian chair as a professor of mathematics. And yet he made incredibly diverse contributions. He contributed to mathematics, logic, philosophy, and engineering. And he died in 1716, sadly in disrepute due to his feud with Newton. It was said that only his assistant attended his funeral. It was, despite being such a monumental figure who's remembered for so many contributions, the dispute over who invented calculus, which we'll go into a bit more, left him in a situation where nobody wanted to be associated with him. In terms of his legacy, things he's remembered for, he was one of the first. He built one of the first mechanical calculators capable of four arithmetic operations: addition, subtraction, multiplication, and division. And this is an image of a replica of that machine. In philosophy, he introduced the theory of monads, which is some kind of fundamental, irreducible type of matter. And of course, like Newton, he invented the calculus, but his version of calculus was better. And I'll explain what I mean. But first, let's go into a quick timeline of the Newton-Leibniz dispute. So, most of Newton's work on the calculus was done between 1664 and 1666. It's pretty universally acknowledged that he was first to assemble his calculus, whereas Leibniz did most of his calculus work in 1672 to 1676. And in that period, towards the end, Newton sent Leibniz a couple of letters describing his binomial series. We saw some of his work on the binomial series in the previous lecture, but it did not contain most of the ideas behind his calculus. So it would be hard to conclude that Leibniz had used those letters to invent his calculus. So several years later, Leibniz published his ideas of the calculus in 3 papers in a journal called the Acta Eruditorum. And those laid out the main ideas of his calculus. And in 1687, Newton publishes his Principia, which also included some calculus computations, though his primary work on the calculus wasn't published until after his death. Then, as we get into the 1690s, there are attacks on Leibniz. People start claiming that he copied his calculus from Newton, and that he didn't come up with it independently. So Leibniz appealed to the Royal Society, which was the central organization of scientists in the UK, and Leibniz was a member, but Newton was the head of the Royal Society. And the historians looking back say that Newton influenced the committee review of Leibniz's appeal, and as a result, in 1712, the committee ruled that Leibniz plagiarized. And so Leibniz's reputation suffered an irreparable damage, and he died not long after, in 1716. And yet, as we said, the Leibniz's version of calculus, infinitesimals, like the dx dy, as opposed to Newton's fluxions, was eventually the form of the calculus that endured. And a big reason for that is that there's something so intuitive about Leibniz's notation that you can kind of read off some of the theorems of calculus just from the notation. So for example, the fundamental theorem of calculus, well, it looks something like this. If you take an integral of a derivative, then you can kind of cancel, you can cancel the dx's, and then you'll be left with this expression, which simplifies to y of b minus y of a. Okay, obviously this isn't a rigorous proof of the fundamental theorem of calculus. It's just something that kind of intuitively falls out of the definition. Something similar happens with the chain rule. If you have, for example, y equals f of u and u equals g of x, then if you want to compute the derivative of y with respect to x, so if you were to write it in Fluxions, it might look something like y dot equals f dot of u times u dot, something like that. I don't know exactly how you would write it with Fluxions, but when you write it in terms of Leibniz, I'm just put a question mark so you don't take that as authoritative. When you try to put it in terms of Leibniz's notation, well, we have dy dx, that equals dy du. Okay, so the derivative of y with respect to u times du dx. Okay, and this is very close to what you would assume just by crossing out the du's, and it happens to be true. Again, not a rigorous proof, but something quite intuitive. Then if we want to try to find arc length formula, so if we have some curve and we want to compute the arc length, so Newton was able to do some of these computations, but it's much more intuitive in Leibniz's notation. You just draw your right triangle, dx, dy, and then this infinitesimal arc length by the Pythagorean theorem will be the square root of dx squared plus dy squared. So if you want to compute the length of the curve, you just have to integrate all of those arc length infinitesimals. And factoring out the dx's, you get something like this, square root of 1 plus dy dx squared times dx. Pulling out the dx squared, applying the square root, you get a dx on the outside. And this integral is the arc length. So again, this is doing things with infinitesimals that you shouldn't really be able to do, like, dividing them and messing with them in this manner, and yet it leads to the correct results. So because Leibniz's notation so closely mirrored what was happening at a fundamental level, it made intuitions behind calculus much more apparent. And so Leibniz's notation was ultimately the one that stuck around, even if Newton was the first to come up with a calculus. And now we're going to look at a sample of Leibniz's mathematics. Specifically, we'll start with the transmutation theorem. And this is a special case of integration by parts. Let's state it. So we're going to So we're going to say we have some curve y equals f of x. We're going to define the function z of x to be given by y minus x times dy dx. And that's the y-intercept of the tangent line to the curve y equals f of x at x. So if we have this point, so this is x, and this is x f of x, or xy, let's say, then this length is z, okay? Then the integral from a to b, let's say this is a, and this is b, of y dx, so just the area under the curve, is equal to half times xy evaluated at b minus the evaluation at a, plus the integral from a to b of z dx. Okay, so integrating this alternative function, which is defined using the tangent line. Okay, and so I mentioned that this is an example of integration by parts, and it's where you take one of the functions to be x. So if you have integral of y dx, this is equal to xy minus integral of x dy, and just some manipulation of these of z and the associated integrals in this equation will show you that you can turn one into the other just by manipulation. Okay, so let's talk about the proof of this theorem. So the proof comes in three parts. First, we're going to compute the area of the wedge in gray and show that that's equal to 1/2 the integral from a to b of z dx. Okay. So considering this wedge, so we're going to compute the area of this full wedge. So full area is going to be equal to the integral of the areas of these teeny pieces, small wedge. Okay. So we're going to start by labeling some of these edge lengths. So we have here an infinitesimal triangle. ds is the infinitesimal arc length along the curve. dy is the vertical side of this right triangle, and then dx is the horizontal side. We know that this vertical length here is z, okay, and we'll label these two other sides p and q. And just comparing the angles that show up in these two triangles, we can show that they're similar, okay? So let's label corresponding edges. We have this edge corresponds to this edge, and this edge corresponds to this edge, and then obviously the hypotenuses are in correspondence. Okay, so we'll highlight that. Okay, so the ratios between these edges should be the same. So we're going to have that for example, z over ds is equal to q over dx. Okay? As a result, the integral of z dx equals the integral of q ds. Now q ds, you'll notice, even though it's a little strange to think about it, or just to view it this way, q ds is going to be twice the area of this small wedge, because this is a triangle whose base is ds, and whose height, when you drop the height to the perpendicular, is q. So we know that 1/2 q ds is equal to the area of the small wedge, so if we want the full area, that'll be equal to the area of the small wedge, 1/2 q ds, but we just deduced by the similarity of the triangles that that's going to be equal to 1/2 times the integral of z dx. Okay, and all of this is going to be over the interval that we're interested in, specifically from a to b. A, b. Okay, so we've checked off this. Again, this is using the similarity of the two triangles in this picture, as well as the formula for the area of a small wedge. Okay, well, how about these next two parts? We're going to need to compute this area. It's the area of a triangle T, and this trapezoid Q. Okay, so this T, well, let's compute where this point is. Okay, so if we have A here and B here, and this is A, f of A, and this is B, f of B, then just considering the line through the origin that contains B, f of B, this line is going to be the line y equals f of b over b times x. So this point will have to be on that same line, so it's going to be a and y coordinate a over b f of b. Okay, so then it becomes easier to compute the area of the triangle and of the quadrilateral, since we have the relevant side lengths. So the area of the triangle T is going to be equal to 1/2 base times height. So the base is going to be f of A minus A over B f of B. Okay, times the height, which is just A. Okay, and maybe I'll put that over here instead. Okay, so that gives us 1/2 AF of A minus A squared over 2B F of B. Great, that's exactly what the formula over here says. That's the area of the triangle. Now let's compute the area of the quadrilateral. So we have area of Q. Because we have a pair of parallel sides, the formula will be given by the average of those two sides times the average of the side connecting them, times the length of the side connecting them. So we have B minus A times the average, which is going to be F of B, right? That's this height, plus A over B F of B divided by 2. Okay, and now we're going to factor out F of B over 2B. So B minus A, let's put the F of B over 2B first. F of B over 2B times B minus A times, well, we pick up a factor of B in the first term, so we get B plus A. Okay, and B minus A times B plus A is a difference of squares, so we have F of B over 2B times b squared minus a squared. And that gives us 1/2 b f of b minus a squared over 2b times f of b. Okay, and that's exactly our area formula for the trapezoid. Kind of apologize for that. Let me see if I can make this a little neater. Okay, a little more delineation here. Okay, so now having proved all of these formulas, what we're left with is the fact that the area of the wedge is 1/2 integral from a to b of z dx. And we have that if we subtract this triangle and then add in this quadrilateral, then we just get the normal area under the curve. So that would be this, the integral from a to b of y dx. Okay? So reorganizing that, we have integral from a to b of y dx equals, okay, so so we have minus t and plus q. What we see is the second of these terms cancels out. So these go away, and we're left with 1/2 x f of x evaluated from a to b, right? Because you're adding bf of b and subtracting af of a. And then we also have on the other side this 1/2 integral from a to b of z dx. And this is essentially our transmutation theorem. Integral from a to b y dx equals 1/2 xy ab plus integral a to b of z dx. Okay? That's Leibniz's transmutation theorem. Let's see an example of where this comes in handy and gives us, it leads us to the beautiful Leibniz series, which one of the discoveries that Leibniz is famous for. So we want to compute the area of a quarter circle of radius 1 in centered at 1, 0 in two different ways. Okay, so we have circle here, sorry, axes here, and we want to draw a circle. Okay, so it looks something like this. Okay, so this is the point 1, 0. And we want to compute this area, so it's a quarter circle, centered here. So obviously, as a quarter circle, it's just going to be 1/4 of the area of the full circle, which we know is pi r squared. Okay, how else can we compute this? Well, we can set up an integral. So we know that this circle is defined by the equation x minus 1 squared plus y squared equals 1, right? That's r squared. Okay, so simplifying, we get x squared minus 2x plus 1 plus y squared equals 1. Let's get y on its own. Putting everything else on the other side, we get y squared equals, okay, the 1's cancel and we're left with 2x minus x squared. And that tells us that if we want the upper quarter of the circle, we're looking at the function y equals positive square root of 2x minus x squared. Okay, so if we want another way to compute this area, it's going to be given by the integral from 0 to 1 of the square root of 2x minus x squared dx. Now, in order to compute this integral, we want to apply the transmutation theorem. So in order to do that, we're going to need to compute z, this the coordinate for the intercept of the tangent line. So we want to apply the transmutation theorem. First, we compute z. Okay, so let's do that on the next page. So we have z is equal to y minus x times dy dx. Okay, so since y is equal to the square root of 2x minus x squared, that means dy dx, applying the chain rule implicitly here, we're going to get half the reciprocal of the square root, so 2x minus x squared, times its derivative on the top, which will be 2 minus 2x. Okay, so that simplifies to 1 minus x times square root of 2x minus x divided by square root of 2x minus x squared. So plugging that in here, we have y minus, or rather, again, plugging in square root of 2x minus x squared minus x times 1 minus x divided by the square root of 2x minus x squared. Okay, so let's put these both over the same denominator. So that just means multiplying the left-hand term by the same square root top and bottom. Okay, so we have 2x minus x squared divided by this square root minus x squared over the same square root. Okay. And so that's going to be equal to, well, 2x minus x is x, minus x squared plus x squared, that cancels out. So we're left with x divided by the square root of 2x minus x squared. Okay, that's kind of nice. We can simplify this a bit more by putting these both inside the square root and canceling an x. So we get the square root of x over 2 minus x. Okay, and that's quite nice because if we wanted to solve for x in terms of z, so at this point we could just square both sides. So we get z squared equals x over 2 minus x, and then cross multiply, we get 2z squared minus xz squared equals x, which means that 2z squared equals x plus xz squared, and that means that x is equal to 2z squared over 1 plus z squared, or z squared plus 1. Okay? Cool. So that helps us start to fill out this transmutation theorem. So let's recall what the statement of the transmutation theorem is. So if we want the integral of y dx from 0 to 1, that's going to be equal to, well, first 1/2 times xy evaluated from 0 to 1 plus the integral from 0 to 1 of z dx. So we just need to get this integral of z dx. And as a function of x, z is a little messy, so it's going to be more convenient for us to use x dz. And we note the following, that let's say we have some function here. Okay. If we have z as a function of x, okay, let's say this is a function which goes from 0, 0 to 1, 1. Z is a function of x, and you can also write x as a function of z. Then you'll notice the area under the curve defined by g of z is, together with the area under the curve defined by f, makes up the whole box. So if I want to get 1, I could just do the area of the box minus the other. So this tells me that, we'll include this as a little lemma, that the integral from 0 to 1 of z dx is equal to the integral, 1 minus the integral from 0 to 1 of x dz. Okay. Great. So now we know what x dz is, so we can say the following. So 0 to 1 y dx equals 1/2. Okay, well, xy evaluated from 1 to 0. So we know that this is x times the square root of 2x minus x squared from 0 to 1, plus 1 minus the integral from 0 to 1 of x dz. Again, x is 2z squared over z squared plus 1. dz. Okay, so that gives us 1/2 times, well, this expression x times square root of 2x minus x squared. At 1, that's just 1. At 0, it's 0. So we have 1 plus 1 minus, and now we have this integral. And Leibniz's idea here was to expand this using what we know about the geometric series. So this can be rewritten as 2z squared times 1 over 1 plus z squared dz. Okay, and 1 over 1 plus z squared has a very simple expression that's going to be equal to 1/2 of 2 minus 2 times the integral 0 to 1 of z squared times 1 minus z squared plus z to the 4th minus z to the 6th, etc. dz. Okay, so let's keep working on that integral. So now we have a couple of 2's and we have the half, so let's just distribute that. So we have 1 minus the integral from 0 to 1 of z squared minus z to the 4th plus z to the 6th, etc. dz. Okay, so here Leibniz makes the assumption that you can term-wise integrate. Of course, as we've mentioned in previous lectures, a lot of this stuff was done without any rigor. Like, who says you should be able to integrate an infinite series term by term? But the fact is, it'll get you to the correct answer. So we're going to follow his lead and get z cubed over 3 minus z to the 5th over 5 plus z to the 7th over 7, etc. And that's evaluated from 0 to 1. At 0, all of these terms are 0, and at 1, they are the fractions with odd denominators. 1 minus a third plus a fifth minus a 7th plus a 9th, etc. Okay, so we've computed this integral in 2 different ways and came up with 2 different answers. And that leads us to the Leibniz series. The Leibniz series is the assertion that these 2 two solutions are equal. So one way of computing the area was pi over 4. The other way was 1 minus a third plus a fifth minus a seventh, etc. Okay? And Leibniz wasn't the first one to come up with this. You could see it in the work of Gregory. I think that in the school of Kerala in India, they had come to a similar conclusion. But Leibniz was certainly the only one to use the transmutation theorem for it. Okay, so in conclusion, Leibniz was a multi-talented polymath, definitely an outsider to the scientific world, but someone who had a lot to contribute. Despite his damaging feud with Newton over plagiarism, his calculus notation was more enduring. And finally, as a sample of his actual mathematics, Leibniz proved the transmutation theorem, a special case of integration by parts. And one corollary of this theorem was the beautiful Leibniz series. Thank you so much.